A very good morning to everyone present out here, distinguished guest speakers on the dais, Honorable Principal Sir, Honorable Dean Sir, Honorable Head of the Department of Mechanical Engineering, Honorable In Charge IFSC, ladies and gentlemen, I take pride to welcome you all in this auspicious ceremony pertaining to AICTE Training and Learning Academy sponsored program, FDP program on application developments in the lab on the chip pertaining to fluid and thermal sciences. So today we have got Professor Dr. Shorin Mitro, who is Professor and ex-Head of the Department of Production Engineering Department of Jadavpur University. We are having with us Professor Dr. Ranjit Bishwas, who is Associate Professor in the Department of Mechanical Engineering of Jadavpur University. So before we start, we'd like to felicitate both the speakers for today's FDP program. So I'd like to request Ms. Kekarana, Assistant Professor of Department of Chemical Engineering, to do the honor on behalf of the institute. Now we are felicitating our respected Professor Dr. Shorin. Now I would like to request Professor Dr. Gautam Bose to hand over the potted plant to the distinguished individuals. Now I would like to request Professor Devdatta Ghosh, Associate Professor in the Department of Applied Electronics and Instrumentation Engineering, as well as in charge IFSC, to hand over the plate to the speakers. Now I'd like to request our Honorable Principal Sir to hand over the memento and a diary on behalf of the Institute to Dr. Shorin Mitra. Now I would like to request Professor Turun Kanti Jana to hand over the memento and a diary to Dr. Ranjit Mitra. So before we start our today's session, let me give a brief introduction of both the speakers. Dr. Ranjit বিশ্বাস, who completed his BTech in Mechanical Engineering from Kalyani Government Engineering College in the year 1999. Later on, he did his Masters in Production Technology and PhD Engineering from Jadavpur University. Apart from technical field of expertise in advanced manufacturing processes, laser beam machining, micro machining, etc., he has keen interest in outcome-based education and different accreditation processes related to quality education in higher educational institutes. Dr. বিশ্বাস is presently working as Associate Professor in the Department of Mechanical Engineering of Jadavpur University, Kolkata. Previously, he was the Registrar of Kaji Nazrul University, Asansol, West Bengal. He also worked as Dean Academic and Professor and Head of Mechanical Engineering Department of MCKV Institute of Engineering. Dr. Ranjit বিশ্বাস is the member of Board of Studies of Maulana Abul Kalam Azad University of Technology, West Bengal, State Council of Technical and Vocational Education and Skill Development for restructuring and modification of the Diploma in UG Mechanical Engineering, Automobile Engineering and Mechatronic curriculums. He is the recipient of National Scholarship, University Gold Medal from Jadavpur University. In addition to member of credits in his account, Dr. বিশ্বাস also received grants from AICT and organized several national, international conferences, workshops, seminars, FDPs, etc. He has published 10 books and book chapters by reputed international publishers and more than 50 research papers in SCI index journals with high impact factor in national and international conference of report. And I am privileged enough, to introduce before you Professor Dr. Shorin Mitra. Professor Dr. Shorin Mitra, I met sir in the very second year classes of ASLAM, Analysis and Synthesis of Machines. And sir is to teach us velocity means a single component and acceleration means two components and one tangential and one centrifugal. So this was the first interaction I had with sir, and I take this pride to introduce my teacher, my guru, Dr. Shorin Mitra, who himself is reputed for his credentials. His field of interest is production technology, non-traditional machining, micro machining, etc. And he has served the Department of Mechanical Production Engineering for long years. And sir has guided a number of PhD candidates, conducted, he was PI of an uncountable number of, research grants, projects, etc. So his daily lecture and his own credential is self-sufficient enough to, unfurl his credentials. So I am very little and pertinent to, and I am his student. So I cannot introduce sir in that way, but sir is sir. There is Guru, he is, PhD guide of Dr. Gautam Bose also. So, Dr. Devashish Adikadi is also there. So, with this, we will be starting, our today's session, technical session, and I hope that the participant will get benefited from the outcome of this, FDP program. Thank you. Thank you very much once again.
कॉपी कर दो सर একটু পেন ড্রাইভটা চেক করে নিচ্ছি। আজকে সেকেন্ড হবে। হ্যাঁ চলো সে নাম পাঠিয়ে দাও। तो स्टार्ट करते हैं। अरेंज करते हैं ওইটা তো একটু লিখে দিতে হবে স্টার্টিং
আচ্ছা এখানে মাইক লাগবে লাগবে না
আমি শুরু করবো। ওকে ওকে শিওর।
All respected teachers, my colleagues,
research scholars present here. A very good morning to all of you. At the outset, I would like to express my gratitude to the management of Haldia Institute of Technology for inviting me here today in this program of ATAL FDP. The theme of this ATAL FDP is something related to thermodynamics and fluid mechanics of mechanical engineering. But we both, myself and Professor Soren Mintro, he is also my teacher, my PhD supervisor. So many teachers were there who worked under Professor Soren Mintro. So we belong to both Sir and myself in the field of manufacturing. We worked on advanced manufacturing technologies, non-traditional machining technologies, micro machining, etc. Yes, these are related to that thermal, at least that thermal fluid. Also, we can connect these manufacturing processes with the fluid mechanics and thermodynamics. Today, we are going to discuss on a topic of manufacturing technology, that is laser-based machining processes and its research trends. That is, what are the research areas of this laser-based machining process. From the name itself, we can understand that it's a process. It is a thermal based process, that is, the source of energy to be utilized for the machining process is thermal energy that is to be utilized for this machining process. So chronologically, if we think on the machining, we can start from the very primitive age, that the progress and prosperity of any society or nation is greatly dependent on the standard of living. We consider this as a parameter, that is, the standard of living is high, means that nation or society is one which is developed one. So progress and prosperity of any nation or society is greatly dependent on the standard of living of the people, which is assessed by the improvement and maintenance of the ample of quality goods and services for the mankind. Goods and services means ample amount of quality goods and services, which includes everything what we use in our day-to-day life, starting from education, entertainment, communication, medical science, everything that we use in our day-to-day life. Those are all related to different services. And for those services, we need to produce different components, machines, different devices, etc., which are to be used to enhance our standard of living. So that way, those components are to be manufactured somehow or in by following some processes. So that way, everything that is the development of the nation is directly related to the manufacturing or manufacturing technologies. From the very primitive age, wood, bone and stone, these were used by the mankind as the tool for shaping different materials for their use during that time. So manufacturing is not a new thing, it is started from the very primitive age. Later on in the ancient Egypt, that drilling and cutting tool, with the development, with the time, these developments have been made. Gradual developments have been made. I am not going into these details of this one. But during that 1980s, from that revolution in the field of this manufacturing had been started in the year during this 1950s. That time, different machine tool we all have, I hope almost all of us are from the engineering background, so we have gone through different machine tools like lathe, milling, shaping, drilling, etc. So from this time, that 1950s, we have started using these machine tools for shaping of different materials, different components with some precision or desirable surface finish, etc. So initially, after that 1950s, during 1980s, different control systems were being included with the machine tools for the accuracy to enhance the accuracy, precision of the components to be designed or to be manufactured. Later in the year during 1980s, 1990s, revolution in the computer and electronic industries accelerated the improvements in machining accuracy and increased demand for components with high dimensional accuracy and surface finish in the range of micrometer. This is all about the chronological development of the machining operations, different machining operations. Why today that LPM, what I have mentioned that we are going to discuss about this laser beam machining process, that is one non-traditional machining process. Also we consider this machining process as one advanced machining process. This machining process, though so many conventional machining processes are there available in the industry, mechanical industry, we still need these advanced machining technologies because of some reasons. Reasons are that machinability factor, this is dependent on the combination of the job, that is the work specimen, and the cutting tool. This machinability mainly dependent on. With the advancement in the field of this material science, so many different materials have been developed in last 10-15 years for the better utilization in different industries like aerospace, automobile, biomedical, etc. So with the development of these newer materials which are high strength, high hardness, okay, this kind of material, here also with the increment in these properties, the machining capability of these materials are becoming difficult with the conventional machining process. So machinability factor of the material is one factor to be considered. Because why this advanced machining technologies have been invented. The second is the job shape complexity. With the time, here so many figures are there. These are very simple figures, hole, different kinds of holes. Like that curved hole, that third one, it is maybe we can visualize this, that this is one curved shaped hole. But generation of this hole is very difficult with normal conventional machining process. But so many applications of this kind of holes and this kind of these features, recesses, these are there in the industries. So job shape complexity is another consideration when selecting this advanced machining technologies. Next is similar to this one, this automation of data exchanges. Automation we know is the control system, basically that feedback system are being incorporated in different machine tools or machines, so that the job accuracy or the precision of the final product, that would be much more higher. Precision requirement is another one. Similarly, machine surface integrity, requirement of miniaturization. Miniaturization we all know that for the proper utilization of the space, also requirement in case of that microsensors, microchip, etc. We need to produce different components of micron level dimension. So miniaturization, demand of this kind of components are very high right at this moment in the engineering industry. So all these 6 considerations can be taken into consideration for the advanced manufacturing technology, use of advanced manufacturing technologies. This is actually the classification of this advanced manufacturing process. I am not going into these details of this one. Basically, we classify this modern machining technologies or these processes based on so many parameters. One such parameter is the source of energy to be utilized. Right? Source of energy means we need to utilize some sort of energy so that machining operation or that manufacturing process can take place. So here one such parameter is the source of energy. Source of energy may be that mechanical energy, like that normal drilling, milling, grinding. Okay, these are, we consider that mechanical energy is being utilized. We convert this electrical energy into mechanical energy, then that mechanical energy is been utilized in case of that source of energy when is mechanical energy. Similar to this one, electrical energy is there directly. Thermal energy is also there. These are different kinds of energies that are being utilized for manufacturing processes in case of advanced manufacturing processes or technologies. this is the selection of modern manufacturing process. What are the basis of selecting this? Different machining parameters are there. As I have already said that source of energy is the basis on which we classify the modern manufacturing processes. Here different machining parameters are there. Like in case of that laser beam machining process, the parameters we normally consider are peak power. That laser we all know is a source where a beam, coherent and monochromatic beam, when is focused on a surface of a material, because of heating, that material removal will be taking place from that surface. So over there, in case of laser beam machining, different parameters we consider are peak power is 1, pulse frequency is there, then scanning speed, that is at which speed that laser will pass on the surface of the material to be machined. This kind of different parameters are there. Similarly for other advanced machining processes, so many different parameters are there. So whether that parameter range for a specific machine or machine tool, that parameter range is a fixed one. For my purpose, for my machining process, whether those parameters are suitable or not, that has to be considered while selecting this machining process. Work material, in all cases, for all machining process, work material plays an important role for getting the desired surface finish, precision, etc. etc. Various output criteria. For every machining, there will be an objective. Let's say one plane is to be prepared through machining process. That plane has to be used for some purpose, right? We manufacture or produce everything for a definite purpose. That component will serve a definite purpose. So depending on the purpose, that output criteria is to be selected. For a simple example, I can give is, let's say, for a plane surface, it may be the surface finish. That surface finish we always want. For the normal cases, it should be surface finish should be as good as possible, or surface roughness we can consider is as minimum as possible. So these are the criteria. Similarly for a hole, if we use a laser source for making a hole, that hole will be a tapered one because of its inherent capability of converging in nature of the laser source. That hole will be tapered in nature, but tapering of the hole is not desirable. So that may be one characteristics or the output criteria. So this way output criteria are to be selected based on the desirability of a particular machining operation. Cost effectiveness is applicable for all machining processes every time, all the time. These are different parameters on basis of which these are selected. This is the broad classification of the modern machining technologies. One is machining, another one is finishing processes. Out of machining processes, I already have said that based on the source of energy, type of energy, thermal, mechanical, chemical, electrochemical, etc. These are classified. USM is ultrasonic machining, AJM is abrasive jet machining, WJM is water jet machining. These are different kinds of non-traditional or advanced machining processes in which mechanical energy is utilized for the machining operation of the material removal operation. Similarly, in case of thermal, one EDM is there, electro-discharge machining. PAM is plasma arc machining. This way, these are the different examples of the advanced machining technologies in which thermal energy is utilized for the material removal process. Chemical electrochemical is there. CM is chemical machining. CM is electrochemical machining. Similarly, this is one kind, hybrid machining technologies. Hybrid is something in which every system or every machining process is having its own advantages and disadvantages. Hybrid machining is something which is the combination of two different advanced machining processes that may take part in direct machining operation, both the processes, or one may assist and another may take part in the machining operation. So that way, hybrid is something is the combination of two or more different advanced machining processes. Here examples are ECG is electrochemical grinding. Different examples are there. Electrochemical discharge machining is ECDM. So many different laser assisted machining, etc. These are there. So these are all different kinds of hybrid machining technologies. Next is the micro machining. We already have discussed about one point, that is the miniaturization. When the dimension of the component, or it may be the portion, the material which will be removed from a particular raw workpiece, if the dimension of the removal is within the range of 1 micrometer to 1000 micrometer, then we consider that operation as the micro machining operation. Right? 1 micrometer to 1000 micrometer range material removal dimension, if falls between this one, then we consider that process, particular process through which we can remove material in the form of tiny particles of dimension 1 micrometer to 1000 micrometer, then we can consider that as the micro machining operation. Different micro machining operations are there. So many differences are there between this USM and that micro USM. Differences are there in terms of their machine configuration, specification, as well as the output criteria. That part is another modern machining technology, is the finishing, AFF, then CMP, EEM. These are different abrasive. First is the abrasive flow finishing, AFF. CMP is chemical mechanical polishing. These are different surface finishing operation. Micro finishing or super finishing we can consider. These are the advanced super finishing. Normal surface finishing operations are also there. We have heard of lapping, honing, rimming. These are there. But these are something which are advanced for used for getting much more tolerance or very accurate dimension, precision machine parts. This is something which I was initially told that we are going to discuss about this one, and what are the research areas so that we can work, or what are the works or research works that have been carrying out in the field of the laser beam machining. Laser beam machining is essentially based on the effects generated at the contact of the workpiece with the laser beam that has adequate energy and spatial temporal characteristics. Laser, acronym of laser. So laser is very it's monochromatic in nature. It can be focused with a dimension of that focal diameter, that spot diameter on which this can be focused may be reduced to 30 to 40 microns also. 30 to 40 micron. I hope you have that understanding about the micron. I can give you one example that a normal human hair, the diameter is around 50 to 60 micron. Okay. So we can convert this laser in a diameter of range 30 to 40 microns also, depending on the requirement or the desirable quality characteristics. We can convert it to a diameter of 30 micron also. So when this is focused on a particular surface, because of that thermal energy that will impinge on the surface, when we come in contact with the surface, the heat will be there absorbed by the material. Because of that, heat temperature will go up. Because of the temperature, when that will go up, so many changes will be there on the surface on which that will be focused, that laser beam is being focused. So one is that changes that will be taking place. One is that material heating up to a temperature lower than the temperature. It is dependent on the energy of the laser beam that will be focused or used for this purpose. If that temperature goes which is less than the melting point temperature, effect will be something. If it goes beyond the melting point temperature, effect will be something else. If it is beyond supercritical, or means far beyond the melting point temperature, then the effect would be something different. So this 1, 2, 3, 4, these are the different effects on the basis of the energy of the laser that would be utilized for this particular purpose. But that machining, as I have said, machining is something in which some kind of material removal will be taking place. For the removal of the material, that is must that 3 and 4, these 2 points, this is must for the machining purpose. Yes, some other processes may be carried out with the less amount of heat to be heated to a temperature less than melting point temperature, that is phase may be changed or some properties may be increased or enhanced of that particular material, but material removal will be taking place because of that melting and vaporization in case of laser beam machining process. And this is also, as we understand, this is one process based on the thermal energy. This is very much dependent on the properties of the material to be machined or to be used also. That optical and thermal properties of the workpiece which is to be used in case of this laser beam machining. This is something which is the thermal aspect of this laser beam machining. We know that parallelopiped, this if we consider of dimension dx dy dz, that is the laser beam is focusing on the surface, top surface. It's not that all of the energy that will be absorbed by the material, that is one part we have considered. Some part will be absorbed by the material, some part will leave from the reverse side of the material. So this is the heat that would be there, which actually would be utilized for the machining operation, which will elevate the temperature of the workpiece, which finally will melt and vaporize the material. So melting and vaporization is the basic principle of the laser beam machining process. That is the material removal in case of the laser beam machining process. Here this is one kind we can, this bell shaped thing. This is actually the distribution. This is the way how that laser is being distributed. The center or axis of the laser, the intensity or the power would be the maximum one. We have focused this part. So this part is normally, if the temperature of or the energy of the laser beam focused is of very, central part will get melted and vaporized instantaneously without any additional or extra means that support, we can say. But later part that will get some melting, this part, this part. Yes, in case of this laser beam machining we use gas jet. That melting will be taking place, but may not be that ejected, that material, molten material will not be ejected. Okay, after this one, this may again re-solidify. So to remove this molten material, gas jet which will flow that gas may be of different, gases may also be used. Effect would be different if it is air, if it is oxygen, different effects on the final output or final job. That would be there depending on the type of gas also. So that gas jet at high pressure, that will be there used to flow the gas to that area, because of which some material in the molten state will be ejected out and that material removal will be taking place. This is the basic scheme of the laser beam machining process. We all know that different types of lasers are there. Solid state laser, NDER is there, NDOIV04 is there, diode laser is there. So many different solid state lasers are there. Gas lasers are there. Gas lasers, CO2 is one kind, CO2 laser. Excimer laser is another kind of laser under the gas laser. Dye lasers are also there. Copper vapor laser is another kind, is newer one comparatively. That is also there. It's not that all kinds of lasers are suitable for this machining operation. In industry, mostly this NDER is one solid state and that CO2 is one gas laser. These two are more suitable, mostly used in the industry, but some other excimer, that NDOIV04, these are low power laser. These are also used, widely used in the industry for different purposes. So this setup is there in Jabalpur University. I have worked on this setup. This is another one. The previous one was NDER. This is ND YV04. This one. This is fiber laser. This setup. This I already have mentioned that so many. This is actually parametric studies of the performance criteria of this one. Of laser beam machining process, quality of cut surface, heat affected zone, as it is a thermal process. These are different output criteria. These are quality characteristics of the finished work. If it is, let's say, a circular hole, that circularity may be another important aspect that may be considered as the output criteria. So, different for the different job, desirable condition, we may have different output criteria, but these output criteria, these are all influenced by the process variables. That is the parametric or the parameters. Those are to be utilized in case of different machining operations. In case of that would be changed or different one. Assist gas we have seen depending on the type of gas, gas pressure, velocity or flow rate. Okay, these actually one parameter, and these are the sub parameters we can consider. This type of gas, gas pressure. So huge number of different process parameters are there, and depending on the when a selection of the parameters, we will get the final output of the result. Rather, we can say depending on the desirable output parameters, we need to select or choose the input parameters to be used for a particular machining operation or the advanced machining process. Now this is not that laser beam machining is something which covers everything. It is having a different types of operations also under this laser beam machining. This is one thing which is laser drilling process. It is widely used on this drill hole laser drilling. Most extensively used one in aerospace, aircraft, etc. etc. Again, this drill hole does not mean that only that laser will be focused on a particular surface and that drill will be produced. It's not that. The drill again can be produced by following a different manners. That first one, if you look, this is that single pulse laser, which when will be focused on a particular surface, that hole will be laser which when will be focused on a particular surface. If that thickness is something which is that laser is capable of drilling truly, then that through hole will be produced in that particular surface. This is something is called trepanning operation. It's not that hole that would be responsible, that focused laser beam is responsible. That normally uses of two different types over the continuous wave. That is why in case of machining operation, normally we use the pulsed wave. So in case of that pulsed wave, it's not that like this one. Number of passes that will be taking place on the machining. This is one research carried out by S. Bandopadhyay and the different researchers. They have carried out this experiment and this is tapering is much more with respect to that one. Tapering is so by controlling the process parameters, we can control this non-desirable or undesirable aspects of the machining operation. Here from this one, we can say that this is something which is machined considering the different parameters like pulse width, pulse energy, pulse frequency, etc. This is something else is the different one in which that tapering is much less with respect to this one. That is another one where characterization of whole circularity in pulsed NDR laser microdrilling of titanium nitride and alumina composite has been analyzed, studied. Circularity is the roundness of the circle, roundness. It's not that exactly perfect circle that would be generated by laser beam. It is not possible. Perfect circular hole cannot be generated by this process, this laser beam machining process. But here in this case, the material removal rate is much more higher, as the power of the laser we use is much higher. So here that circularity means that roundness that has been measured here in this one. In this paper it is cited that characterization of the whole circularity in the pulse and laser micro drilling. These are the different variations they have shown with respect to, this is actually the graphs showing the effect of different parameters on the output criteria. Like here in the first one is the pulse frequency is one parameter, that is tapering, that tapering of the circular hole, that is explained here in this one. Normally this happens when pulse frequency gradually increases. In general case, that tapering gradually decreases, that taper value. So this value, when we are increasing this pulse frequency, it's not that maximum pulse frequency, if we say we'll get all values on a desired or the perfect one. It's not that. If we increase this pulse frequency, maybe some other output criteria will be there which will be adversely affected with the increase in this one. So that has to be optimized. That optimization has also been done in these papers. This is one kind of operation we can consider is the laser drilling, where drilling is a process, machining process, by using this laser source. These are similar kind of these are the micrographic views of the drilled hole. This is one thing. This is the hole, is the diameter. This is D max. This portion is the heat affected zone. That also can be studied as one output. It is not desirable that heat affected zone of a particular surface or material. These are the micrographs of microscopic views of the microdrilled holes with high and low hole circularity and exit. Yes, circularity can be measured on the top surface as well as on the bottom surface if it is a through hole, because on the both surfaces we get that circular means impression of the hole. This is second type of operation that can be carried out with the use of the laser beam. It is instead of drilling in a single spot, it is cutting. Cutting means that either laser beam or the workpiece, any one out of these two has to be moved, okay, along the axis through which it is to be cut. So this is the scheme of this one. Scheme of this laser beam cutting, laser cutting. Here these are the variations similar to this one. This is one research paper in which this different aspects of output criteria, that is surface roughness, on different parameters, how these parameters influence the output parameters has been shown here. This is another cutting speed is another input parameter. Shown this surface roughness values change in variation in surface roughness values on this one. This is also on cutting. Next is another one is right now it is growing in interest because this grooving and channeling, this is having high demand in microfluidics, in the field of microfluidics, especially the micro channel on different materials. Okay, this is having high demand in the microfluidics and other sectors, engineering sectors. So this is something is cutting off groove, okay, cutting off groove or channel on a particular surface. That channel again can be cut by moving the laser beam on a particular surface, so that material will get melted and vaporized from the zone on which that will come in contact, that laser beam is coming in contact. But another way is also there through which we can cut the groups. Like here, two different laser beam may also be focused, so that here this triangular shaped this kind of groups may also be produced. This is one laser source. This another laser source may be all utilized together, so that a triangular or different other shapes can also be cut. This is something which is called grouping or channeling. These are the different aspects of this similar kind, that variation of different output criteria or quality characteristics of the microchannel, that width, depth, from here we can understand that what is the width or depth. Width is something that here, if you consider that width on the top surface is the distance between this and this, that top portion, that curve width or width is this one, and depth is something which is this one. This figure actually shows the variation of the width and depth with respect to number of passes. It's not that in any machining operation or process it is applicable. Like in case of stepper, if you say that we need to, let's say, remove a particular thickness of the material, it may not be possible to carry out that whole depth of cut removed in a single pass. Okay, so we, depending on the specification, also depending on the surface to be generated, that accuracy, okay, we need to select the depth of cut. So we need to pass number of times so that material will get removed from that particular surface. So here also, depending on the thickness and the height or the depth of the channel to be made, we may need to go through a number of passes. Here this shows the variation of the depth and width with respect to different number of passes, pass 1, 2, 3, 4 and so on. This is continuation of this one, is number of passes, is this one. Surface roughness, we can conclude from this one that surface roughness gradually decreases if we increase the number of passes. This is one same image of the center of the microchannel. Which is very special one in the field of the laser beam micro machining or laser beam machining. As we all know that it is a kind of source monochromatic in nature, can be focused and directed a long distance without any deviation. So it's not possible to cut or carry out any operation on transparent material, because if we focus laser beam on a transparent material, that will pass, okay, depending on the transparency of that particular material to be used. যতক্ষণ বলবো
another 15 minutes 10 to 15 minutes
Okay, so it is not possible, we can say, in a normal procedure, by following the normal procedure, to carry out this laser beam micro machining operation on transparent material. But this is something in which we have conducted this laser grooving or micro grooving, we can say micro channels. We have cut on a PMMA material which is transparent in nature. So for that one, we know that some surface is required, that optical and thermal properties it is greatly dependent on. So we have used something tape, that black tape as the absorbent on the lower surface of the material, that transparent material. So one material which is transparent in nature, but on its bottom surface one absorbent material, black in color. As you know that black material can absorb the maximum energy, thermal energy. So used, and it is successfully that carried out, that experiment is been carried out. So these are all different aspects of the microchannels cut on the transparent material. Okay, this is one experiment which is not very common in the field of laser beam machining, that cutting or that micro grooving or microchannel process. Another one is plastic wetting process. In case of fusion, two edges which are to be welded together get melted, and after solidification a continuous bead would be formed, which actually will join to two metals. Joining is very difficult in through every processes. Normal welding processes are also not capable of doing means welding of these similar metals. It's not very easy one. So here laser welding is something that joining of two or more sheets or metal sheets together with the use of the laser beam. So here is the basic scheme of the laser welding process, and these are the microstructure of the joints at various. Actually, this is A and A dash. Difference is one is the micrograph of the microscopic view of the top surface of the bead, and the B or A dash, sorry, not B, and A dash is the bottom surface. That same weld bead, but the figure is the photographic view of the lower part or the lower side of the weld bead. So these are having been done at different working power, that 450 watt, 500 watt, 550 watt and so on, using the laser source of this much of energies. And these are the different analysis carried out, that again analysis, this kind of analysis are based on the output criteria. What is my desirable output criteria? Our aim would be always to get the maximum output criteria as possible. 2, 3, 4, 5 different output criteria may be there, output criteria or quality characteristics we can say. Here is the weld width, is this one, cracking rate is another one, is considered here in this study. These are the variation of these different characteristics with respect to different parameters used for this experimentation. So many physics is also there behind this one, because that thermal conductivity and other optical and thermal properties that maybe means varied with respect to different input parameters. So these are the figures that shows the output. This is something which is hybrid machining process. As we are talking about this laser beam machining, this is one process. I am going to show one example as one example. These are the two different types of hybrid machining process. One is in which all constituent processes, that is, I already have said that it is a combination of 2-3 different processes, machining processes. So here first one is some HMPs in which all constituent processes are directly involved in machining operation, and second one is something which will assist to enhance the material removal rate, but directly that will not take part in the material removal or machining operation. So these are the two different kinds of hybrid machining operations. This is different interactions that can be carried out. This is thermal, chemical, mechanical is the source of energy. Those are the different examples. Now the combination may be this, let's say if we consider this ECDM. ECDM is electrochemical energy and thermal. Okay. Electrochemical discharge machining is one kind of machining. I don't know whether you have heard of it or not. You must be knowing this, that ECM and ECDM are the two different non-traditional machining operations. But here in this case, ECDM is something which is the combination of ECM and EDM. It is the electrochemical discharge machining. That is objective is to eliminate the disadvantages or limitations of both the machining operations in this hybrid machining process. So here this varieties of combination may be done, but it's not that much of established machining operations. Yes, people have tried some combinations, but still work is going on in this field of hybrid machining processes. These are the different examples. These blue colors are all related to the laser beam machining process, laser assisted EDM, assisted turning, laser assisted turning is LAT. These are different examples, these are other different examples. This is one thing which is laser assisted EDM. In very brief, I can say that laser beam machining is having advantage of higher material removal rate. Right? Material removal rate is one important aspect in any machining operation. So material removal rate is higher in case of laser beam machining, but that is lower in case of EDM, electro discharge machining. Right? But the surface finish that is obtained in case of EDM is higher, better than the surface finish obtained in case of laser beam machining. Right? So disadvantages of this EDM and disadvantage of the LBM, both these can be eliminated if we combine these two together. How? That laser beam machining and EDM is LEDM, that is laser assisted EDM. So in this case, let's say one circular hole is to be produced, this kind of circular hole. Initially, if we go through the laser beam machining, that some internal part, that if we remove with the use of the laser, that material removal rate is higher in case of the laser beam. That can be, internal part can be very easily done. But that surface of the hole to be generated of the desired dimension, that part if we carry out that operation with the use of the EDM, then we can combine these two together and that machining operation can be carried out, in which material removal rate would be higher than EDM but less than LBM, and the surface finish that would be generated is almost similar to the surface that will be generated by the EDM and better than the LBM. So that way, this is one laser assisted EDM is one hybrid machining process in which we can combine this laser beam machining process and that electro discharge machining process. Here from this one we can see that this part can be hole can be made with the use of the laser, and rest part is the EDM that can be used. Similar to this one, so many other combinations may also be there, like electrochemical machining and grinding. Electrochemical grinding is another process. So many different processes are there. This is one research work has been carried out by some researchers on this. LEDM is a comparatively newer technique, this hybrid machining process. And latest another process has been invented is sequential machining process, it's called. It's more advanced than the LEDM also. So here in this case, similar kind of that outer or output characteristics, effects of the input parameters on the quality characteristics. These are being carried out in this research work. This is something is the microscope, same images. These are the same images of the microholes produced on a standard micro EDM process. Is the first one, that A. This is something which is carried out from the figure itself, means this photograph itself. We can understand that the surface finish produced by the micro EDM is much more higher than the surface finish that may be obtained in case of the laser beam machining. But here the material removal rate is very less, but material removal operation has been carried out with respect to that laser assisted electro discharge machining process. These are the some advancements which I already have been covered in my lecture discussion. Thank you. It is not a difference. Grain structure, data exposed to the air, data is not exposed. The distribution is great. No different.
Okay. So now we have interaction.
Thank you.
The topic of discussion is exploring micro manufacturing processes with focus on names. Why this topic? Because actually the FDP that you are having is on lab on chip technology. Okay, and mainly on focuses on fluidics and microthermodynamics. Okay, so basically I am not a person belonging to this area. They are core area of research, mechanical engineering. I am a manufacturing person, right? So I will discuss about because of micro manufacturing, but how micro manufacturing is related to this. Okay. See, this is the core thing. We discussed about fluidics, thermodynamics, etc. What are the applications? Engineering is all about applications. Right? You have to make products, you have to deliver processes. So, particularly for manufacturing purposes, so these two areas have got so many applications. And applications relates to the products. Okay. Since we are having not much time, just easy. Okay. How manufacturing affects this? In the title I have explained micro manufacturing analysis means micro electromechanical systems. And this is definitely related to lab on chip. Because lab on chip is one of such immense applications that we are having nowadays. Recently there are two news that was of time concern, or say that I was delighted to have. One was that as a part of our Make in India project, which stays on manufacturing, because we are India with so many populations and demands of products, we are lacking in manufacturing. We used to import and all these things, particularly import technology. But nowadays we are developing, particularly last 10 15 years, we have made tremendous progress in having our own infrastructure, making our own products. In the day, one news was that India is now manufacturing Apple iPhones. Okay, which is not there. Earlier we have the manufacturing base of China and so on. So now they are having this. Moreover, we are now manufacturing chips for mobiles and all this. So manufacturing of chips is very important. So all the mostly developed countries are having this facility. We didn't have, we used to import like that. So that is one. Manufacturing of chips gives that impression that we are at the higher level of manufacturing of this. Second thing, the news that came, you have all heard about Elon Musk, okay, owner of these EV vehicles, and he is doing so many things. Another one of them is he has started a company where he is making chip that will be implanted in human brains, which will have control on that. Because with our natural brain, we are making all these actions and activities. Now, suppose someone gets damaged, or the brain is dead, or due to accident, some part is damaged. What is that? So far, the development is we are making the artificial limbs and all these things. That's fine. What about the control part? Now we are in the position to make those chips which are implanted, and some of the normal activities can be restored. So the topic of your FDP, that is highly relevant up to the time, because this is going to be the future, not only in medical industries, but everywhere. AI has come in a big way, right? There is some apprehension there will be loss of job. Okay, somewhere there definitely that will be there. On the contrary, it will create a huge quantity of new jobs and all these things. But the core is again coming back to manufacturing, right? So as a mechanical engineer, most of us which are manufacturing engineer, we must relate to that. So what is manufacturing today or yesteryears, and what is going to be, and how we have to adapt to that and change our manufacturing infrastructures, teaching level at the academics as well as in the research institutions, then the industries, because the academy is supposed to lead and guide the future, right? So today, with the time that I have, I am going to just discuss and go through this ever-changing way of manufacturing and how it should be in future, particularly in the domain of this lab on chip or chip manufacturing. So that is related to micro manufacturing. Again, to go through that, so it is definitely a part of advanced manufacturing. And we know all mechanical engineers and all this, that these are the mainly things that we concentrate. Okay, we do the machinery study. You have to make a product, get the material, we process it, and that's why it should be machinable, whatever process that we use. Then we develop the products, and development of any product is not enough. If it's a precision product, quality product, maintain the quality levels, the accuracy, the dimensions, the finish, etc. But there is a new domain of manufacturing, micro manufacturing, because there is a huge demand of such things in various advanced industries, space research, medical applications, and aeroplanes, everywhere. And biomedical applications is coming in a big way. When I was a student, the industry was absolutely different. Mechanical engineering means the other machines go and manufacture and all this. We never thought or related to the medical application and all this. Separate. Then the application came, hardware application and software application, then came the application of different softwares in a different way, and so on and so on. Now, then there came making of lighter products where not only the mechanical things should be there, the electronic part should also be there, the control of manufacturing changing in a drastic way. So that is this. So micro manufacturing, again, there can be so many things. Initially started with tool based, and it's turning to micro turning, milling to micro milling, grinding to milling, changing the dimension, smaller size. That is okay, but there are so many difficulties in making a normal turning to a micro tool. Material won't be the same. Its applications, forces, everything will change. The entire metal cutting thing gets changed. So that is one sort of a research. It has been done, it's still going on. Another thing was beam based. No physical tool. They apply different beams. Laser beam, electron beam, ion beam for processing. Now, instead of machining, we are changing the word. We are taking processing. Okay, maybe removal, maybe addition like that. So that is the application still going on. And micro parts can be made by using both of them. Then comes from micro is not enough. When we move to the medical applications, we are going further. Nano fabrication. We are not nano machining. We are not using the term, or nano manufacturing, nano fabrication. Why? Because the way it is made is changing. Okay. So this is this way. Okay. So we are moving contact to non-contact type of machining. Machining to manufacturing. We are also changing the word. Chip formation, removal using chip. That is a contact type of machining, giving formation of chip to chip-based manufacturing. Non-contact, non-traditional machining. Conventional to non. You have to hybrid, combine two machining processes, manufacturing process to get a better output. All are related to product requirements. Why you are changing? You are changing for nothing. Because production economics is very important. You want to go and experiment, the product could go high, it is of no relevance to the industries. Normal to micro manufacturing. Normal size products, small size products, how to go, how to make it. So definitely the process, mechanics, everything will change. So that is an expertise and requirement. Micro components. And micro to nano, another domain. And there is huge application, academics, research, industrial development and all this. And finally, subtractive to additive. Now micro manufacturing can be both in the subtractive mode domain, also additive domain. And you have a thing where cutting down, getting the finish. Other way, you have a thing you go on building up. So additive manufacturing is, those who are in the mechanical or manufacturing engineer know it is the keyword nowadays. Probably everybody is trying to do something in additive manufacturing also. So many things are there. Now coming back to this topic, that is lab on the chip. What is the actually, by the time this is the 4th day, so everybody must have heard the word again and again. So basically it's a miniaturized laboratory system creating on a very small space. we're calling. So definitely, you have to do that. You have to come back to the micro. You have to manufacture this. What you have to do? What are the process on which you have to stress up? How to do that? Whether our traditional machining definitely will do, or to miniaturize this. I mean, tool-based micro machining will do, or we do beam-based micro machining, or whatever else is do. Definitely, there are other processes because those two processes are not suitable anymore. Okay, so it's basically creating small sizes and extremely fine substrate surfaces that we are making. Okay, and creation of microscopic devices. So normally the concept you hold it and do it, or contact or non-contact, so that is not visible. Even the environment of such manufacturing, we are not calling it machining. In that case, it's also difficult because it has to be vibration free, dust free, everything. Even the cost of such laboratory will be huge, and of course the investment, whether it is in the academics or the industry, will be higher in the level of crores. So what are the things? So basically you are manufacturing 3D structures with different applications, okay, and there are different domains of such manufacturing. We can do mechanical micromachining, that is micro turning, micro milling, micro grinding. So in that case you have to have miniaturized cutting tools. You have to provide the mechanics, that is the cutting speed, feed, depth of cut. You have to choose cutting tool materials and all this. You have to develop the micro machines for that, and it is difficult. Physically, it is definitely physically normal cases are difficult. When it is in the smaller space, in the micron level, we are removing material. It is still difficult. So someone is asked what's the difference between micro machining and normal machining. First is the unit removal that you are doing. Here, when you give depth of cut, I mean, everything is in drawing in a millimeter. They are only in micron. So it may be required to have a turning with a layer of 2 micron. So that will be the case. So the tool size will be also in micron. So how to do that? So, but still there is a domain where this is being done actually initially started. Simultaneously, you have to develop that machine tool which can provide that. Otherwise, it will not be there. Beam-based applications are there using different beams. I think he was already talked about how laser beams can be used. In fact, laser beam is a very popular thing used in so many cases. Removal, subtractive manufacturing, additive manufacturing, measurement, inspection, everywhere. Even the microscopes that you are using, whether atomic force microscope or scanning electron microscope, we are using laser beam for that to determine the surface characteristics. Also lithography and etching. These two are very, very popular and recommended manufacturing process on making that thing. That is the chips, MEMS particularly, or a lab on chip type of thing, where the entire features can be developed on them. So, though we have in our mental set of manufacturing of as a mechanical engineer that either the metal cutting set of operations, the processes, or the non-traditional process like EDM, OVERDM or electrochemical dissolution sort of things, a lot of them are there. They are no longer applicable or effective when you are doing a lab on chip type of thing. So you have to search for newer things, and these are the things. This is an additive development of basically where you are using X-rays for these processes. I think all of you must be, some of you must be associated with that. So in general, we are talking about the MEM. So what is there? Mechanical elements are there, sensors are there, actuators are there, different electronic control elements will be there, and mostly we will use silicon substrate. We may use glass also sometimes, it is a requirement. And functions are all well known that they will sense and generate the data, and use it as a control, and the actuators will actually provide the displacement velocity, whatever that is required, and they will perform accordingly. And these are some of the components, and this is just only a few. There are thousands of such components that are being manufactured by micro manufacturing using different methods. The spherical lenses, micro turning, these are tool-based things. Micro motors are being developed, mirror assemblies being developed. Even this is a set where a number of such micro gears are being done, and they have to run on these things. So when you talk of a small chip where these mechanical parts, electronic part control, everything is there, imagine what should be the level of manufacturing. And main concern is what is the process that I should use such that I can get the qualitative output from there. So that is the main concern from other manufacturing engineers. Okay. And in some cases, this is a lathe, micro lathe. So this one that we talk. Okay, so if you do a micro machining part, and you have to make that thing, and just making of anything is not acceptable. It has to perform its duties, intended functions for which it is made. Or a micro factory where multiple number of machines are there, and which are being run like this. Okay. So accuracy is anything. This is true again in a high. On the 12 micron can be much less than that. Tolerances will be very low, and like that. So we have to deal with this category of manufacturing. So you have to have in mind, and accordingly we have to search for the processes or operations. Okay. Now another thing, so far as micro manufacturing or manufacturing of means is concerned, there are two approaches. Okay. One approach we are calling the bulk micro machining. That is, thing is there, then you are doing whatever removal and everything, and finally you are generating. And as I told you, that it will not be doing any shaping operation or something like that. You will be etching mostly in this case. So you have the block, you are making some diffusion and some material, then you are doing some masking operation, then we are doing etching, etching away of this sort of a chemical application sort of a thing. Those who have already know that etching what is there, actually non-traditional machining, chemical machining are already there. So that is being not in that level, it's been further developed to make etching as one of the special process for making micro applications. Okay, so two things are there, two approaches. One is a bulk, that means you have the thing and you are removing the entire thing and getting the final. So this is the product, cantilever, freestanding cantilever in the micro. There can be alternative, which is being nowadays more popular, is over surface micro machining. So we are not removing only, we are adding up. So this is one. So this is a special layer being developed. There is some etching, then again some deposition, and then again finally etching, and finally you are getting this. Okay. So this is surface micro machining. For what purpose? For making those names or micro components, or sort of a lab on chip you can make that. Okay. Now, what are the recommended things? Basically, three categories here: deposition, lithography, etching. Okay. Though deposition is not a very new technology, process, technology is going updated again over the years. It is what was there in earlier days, it's not like that. For example, I tell you that when EDM or electrochemical machining or laser beam machining, all these things came, they were nothing new. The concept of the theory of EDM was there, discharge mainly. Then the electrochemical dissolution, which follows Faraday's laws of electricity, it is there, very old, nothing new. Electron beams, laser beams there. But the technology of using them for a controlled removal of material as per our desire with quality features defined. So that technology, that means to develop the power supply required, to have the flow of electrolyte in case of ACM, or in case of EDM, that dielectric material. So these are the technology developed and upgraded over, but still research is going on in respective areas. And those who work in this area know new papers are coming, and you also contributing to those areas. So they're coming up. Similarly, deposition, lithography, etching. Etching in the form of chemical machining, it was there. You put a mask and this thing and it's coming. But what about normal such component? Still it was difficult because of overheating and loss of tolerance and everything. But to do for micro components on a chip, but all the features are there, that amount of control, since that was not there. So that technology is being developed, and to certain extent is there. Similarly, application. Our old cameras, you remember, so you used to have a reel, it was difficult, then you have to click it and you have to develop and all these things. So similar type of thing is we will be using a lithographic process, but not so simple. Lithography, photolithography is a very popular process so far as micro and also nano applications, nano fabrication things. Similarly, deposition. And deposition in so many forms, by PVD, by CVD, through chemical reactions and through physical, the vapor and all these things. Okay, and there are some sort of castings for polymer materials are also there, and there are other things like thermal oxidation, electrodeposition, so far as this, where the chemical reactions takes place. Lots of options are there, but another thing that comes with that, lot of options, lot of processes are there, but where to apply which one, that is very categorically specific. Like say, when you have a lathe, You have a cylindrical job, that is the thing, and that must be accommodated within. If you have a tool, you can do turning, drilling, everything on that particular machine. So it's a general purpose machine. Similarly for milling, grinding, all these. But in case of this, they are product specific. You have a deposition thing and anything you cannot deposit. No, it's not like that. So that's why application also is changing. Now, thin films. So one of the way of making micro component, micro parts is by depositing thin films on the surface. So you control the size of the film, okay, its thickness and layers and everything. Okay, how? We can put different gases, make chemical reactions. The substrate the thing that we are going to have as a coating, we generate and allow it to settle on them and remove the exhaust gases. So this is one way. Other way is a physical vapor deposition. Nothing, no chemical change. Keep the material, heat the material, create the vapor, allow the vapor to deposit. And both have positive and negative sides, but both are applicable and being applied nowadays. Even some of the labs may be there conventionally where the PVD is CVD, because in our case for normal manufacturing, coated tools were being manufactured by this physical vapor deposition and all these things. But for micro applications, it's much more specific and quality wise has to be more precise. Okay. Now, what are the things that we require for deposition? What is the deposition rate? The deposition rate has to be very, very small because the components are very small. At which rate material is going to be accepted? Then the humidity, that is the quality wise, this parameter is very important. It is not only enough that we have a system which creates and we have a deposition. It has to be an industrial product. It has to have certain quality of benchmark. And there is a uniformity of the film. How uniform it is, the thickness wise. Or run to run uniformity. One layer and another layer. Okay. Though nowadays we have separate additive manufacturing process to do that. On what material? Which layer we are going to deposit? Because that thing will be decided by the product designer or the chip that you are going to make. So one material is there on which we require a specific. Sometimes maybe polymer, sometimes maybe dielectric material because you are going to create a insulative layer and all these things. So which is the manufacturer, I am not going to decide. It's going to be decided by the product designer or the requirement. So accordingly, whether the process is eligible for that or not. Okay. And there are so many other quality characteristics, large number. So it is not a very easy process actually. And the control is very much required, particularly for impurity level and all these things. Particularly in case of the CVD process, where a lot of gases are involved, there may be hydrogen and everything going into the deposition and making it brittle and all these things. And so many other things are there. Okay. And directional, non-directional like this, as you can see from the figure, that this is the estimating so far as the thickness of this thing is concerned. This is not a way because the thickness is changing. Okay, it's not that. But if you are going to put something inside, then lifting of characteristic, this is good. So accordingly, which one I want as per applications, I should go for that. Similarly, so these are the two applications where see, this is metal on, there are depositions are there. Okay. Constant thickness on horizontal and vertical surfaces, this is good. But on the other side, this one, see, vertical step coverage is not good. And mind you, all these are in microns. So maybe 2 microns, 5 microns. So we have a process, we are generating vapors either by chemical reactions or by physical generating the vapor. And there we will be allowed to solidify on that. And so input parameters have to be controlled in such a way that these things are maintained. So that's why our research or the application changes. It is not like that in case of leather operations, we are changing the RPM or depth of cut or this, and you are having the required amount of surface finish or the machining rate like that. So that is there. Similarly, these things have been developed or still going on for specific materials. material combination is very important. Not that any material can be deposited on in this. So a lot of research is required and still going on. Similarly, there can be, that is the aspect ratio can be one of the factor, that is what will be this width to height. So how deep you can go and how much accurate, good quality coverage it can, coating it can make and so on. Okay. See, the void is created there, so there is a tapering effect and all these things, pore filling and all these things are there. Okay, normally pore filling and this gas entrapment method void used to freeze on a normal casting, that is a normal our traditional manufacturing, but still there if we have this sort of things. Okay, the voids are created on this. Okay, like in casting also, we do not have any control. Once it is poured, so we design the flow path in such a way that minimum thing, and the gases must come out. Similarly, in case of thin film generations, the flow of gas and everything has to be controlled in such a way that the flow rate of flowability of the port that is being deposited should be such that this should be minimum. So, quality aspects are different. Now this is the schematic diagram for the chemical vapor phase. So you have the substrate on which you are making the coating, and you have different gases, source gases and everything here reacting and allowing to it. So the time of operation, what type of gases should do, and what is the coating material, and what is the substrate material, what is the sticking ability of these two surfaces, all these things are prime importance, and this is being done. And also the entrapment of this exhaust products, gaseous products into the reactor. So these factors are of prime concern. Okay, so these are some of the other figures which shows how it is to be done. So there will be a lot of gas inlets from there depending upon what type of material you are generating. Say silicon chloride to hydrogen, and silicon is being deposited, segregated out of there, and that will deposit on this. As I said, the exhaust gas will come out like this. So it more or less, though it's a manufacturing, but
catch that. Could you try again?
it is sort of it looks like a chemical laboratory, isn't it? Chemistry lab sort of a thing, but it's a mechanical manufacturing, micro manufacturing, you know, these things, and the dimensions and everything is to be there like that. And there are a lot of options of different types of CVDs also there, depending on what pressure is being done, atmospheric pressure, low pressure, then plasma enhanced things and so many things. And this continuity and the thickness of the coating, they are also prime importance. Okay. And CVD has got added advantage over the PVD process because it creates a very good coating. High growth rates are also there, good reproducibility, and hard to evaporate and all these things, but they have other drawbacks like the temperature has to be high, and because it's a chemical reaction, exhaust gases will come up, and how do you deal with that? That is also prime concern. So both plus and minus things are there. And there is a lot of reactions. I mean, if you have different type of coatings, you can generate by different type of chemical reactions. Okay, as usual, it's a case of chemistry, by oxidation, by reduction, by thermal deposition, compound formation, etc., etc. So you have to again go back to, I mean, in some of the cases we found that in our academic curriculum, chemistry has been exclusive from mechanical engineering syllabus. But if you want to study this type of manufacturing, definitely again you have to go back and have chemistry as one of the subjects, otherwise can't be. I mean, because manufacturing at high level, we cannot differentiate purely mechanical things. So it will be chemistry, it will be metallurgy, it will be electronics definitely, and computer is there everywhere. So otherwise the laboratory, it will basically you will differentiate some product manufacturing you are doing or some chemical processing you are doing. Okay. So at that level you have to adapt ourselves to the basics of all these things. Okay. And so temperature, what sort of crystal is formed, that is epitaxial, polycrystalline, amorphous. According to the requirement, we have to go by this. So definitely they are in the process of developing handbooks, like our normal manufacturing, what type of food, or what type of material, I mean, workpiece and cutting tool combinations that we have normally, we follow what sort of inserts to be used for milling or what type of material. Similarly, for this type of operations also you have these things, you have required this type of input gases or for generating this type of temperature and all these things. Okay. And these are the type of sources. There can be different type of sources depending upon the requirement. Gaseous, volatile, sublimable, combination of these things. Okay. And there are also some requirement, chemical requirement, low toxicity, stable room temperature, sufficiently volatile means heated because you have to form the gases and everything, reaction temperatures. Okay, and sometimes, again, as I was telling, you have to go back to the basics of chemistry also. And there can be atmospheric pressure, low pressure, plasma elements, metal organics, these are different groupings also there. Because coating technology, earlier it was there, from there it has come, but now it is the challenge to apply to develop these MEMS of micro systems. Okay, and both have, all these categories have their probable applications and pressure range, temperature range and all these things. Okay, now other option is much easier, it is physical vapor deposition where we are not having any chemical reaction. So have a solid material, heat it, evaporate it and allow it to deposit. So evaporation is a natural phenomenon. Only the possible temperature has to be there to hit the material to the evaporation level. And there are again two options, evaporation and sputtering, where there is a normal humidity and liquidity will evaporate. Otherwise, you are bombarding with plasma and generating that things which will go and evaporate. So quality wise they will be different. And evaporated use of electron beam is one of the popular options. And for evaporation, normally you require a vacuum for a proper evaporation there, and for sputtering, vacuum is not required. Okay, because that energy level is there on the related deposited elements. This is a very simple diagram showing how it can be done. So this is the product, I mean the wafer on which you require the deposition, and this is the crucible where you are, this is the workpiece holder, and this is the crucible where you are keeping the solid material, and you are heating. And the heating may be in a different way, you can have a resistivity, depending upon the temperature it requires to melt and then evaporate. It may be a resistive heating, inductive heating, like that. But the best heating that comes is obviously electron beam. Okay. And that will go on and go get deposited. This is this thing, and then on the surface that will go on. And like the CVD process, it has also recommendations, that is the material, minimum evaporation temperature, state of evaporation, recommended crucible material is very important, because I have a container, I am keeping the material, then I am heating. So obviously it is becoming in the higher state liquid and everything, so there must be should not be any chemical reaction these two at a higher energy level, neither there should be sticking and all these things. So that combination is also there. There should not be any sort of affinity of these two together. So that is another requirement. And the probable deposition rate in terms of angstrom per second. And if it is an electron beam you are using, so what is the power that is required? Okay. Now earlier in micro machining we used to have electron beam machining, that is one part, but this is another absolutely different sort of applications. Now these are the materials that are being used for PVD. This is a pretty harmless sort of a looking thing. You can have this, but that you have to keep in the crucible and then heat it. Okay, so that's why PVD is much affordable or easily done thing. Okay. So as I was telling you, we can be thermal evaporator, electron beam evaporator, inductive heating also be there. So it's the inductive one. So this is the thing, this is the crucible, and you have the solid material inside. And you are heating, and that is becoming more, and then is evaporating. Okay. But the time of heating, the rate of evaporation has to be precisely controlled. Otherwise, you do not have that layer of deposition which we need in 5 micron, 2 micron, 10 micron maybe. So that has to be precisely controlled. Otherwise, you cannot have industrial product. So industrial product means absolute quality control. Anything we can generate in a lab and say it is working. But if you want to sell the thing, use for certain purpose, so that has to be done. Unless it is a very customized market. So this is another. This can be also sort of a holder type of thing. You fix it, and this is a crucible, and where you can keep the job solid material. help and could be there. Physically going to be evaporated. Okay. Now this is an EVM evaporator. Okay. There will be a strata, there will be place for fitting the material and all these things and outside control. Now all these things, even in case of PVT, the equipments are very costly. So that is another, that is the main drawback for academic institutions. How to have such a fund to create a laboratory. You know theoretically what is there, but in that case, in research institutes, particularly central institutes, are an advantage. They have huge fund, and I have seen in so many places, they have them, but each one of them are very costly. Okay. And again, these are some of the temperature ranges. These things are there available. Thermal evaporation, electron beam evaporation. So these are very important so far as PVC is concerned, because you need the containers, the crucibles where you can keep it. And what should be the heating coil type, if it's a resistive coating, what should be the shape and everything. Because as a manufacturer, you don't need to manufacture, you don't need to make the machine, you need to operate. These are the physical things that you want. Theoretically it's okay, you wait till you generate, this will be the temperature, okay. But how to do that? You provide the heating coil. So what should be the heating coil? Where it's available? What is the material? What will be the length? So that's the question we must ask. To make it or to use it. Then what should be the material of this crucible? What should be the size? What should be the shape? Okay, like all these things. But normally these are the things where depending upon also it will depend on the product. Suppose you are going to make a lab on chip or a base. It will have its own shape and size. On that you have to make a coating. And accordingly you have to design, you have to choose and all these things. Okay. So these are some of the things, and the evaporation pressure and all these things are related. Ceramic materials. Okay. That is the crucible material where you are going to keep that. And their evaporation temperature, their melting point is important, because if you are heating the material and that material and the crucible temperature, if it is melting temperature nearby, then it is not recommended, because it itself will get eroded. Okay. Yes, I am going to that. Okay. This is something else. So that was deposition. So by that method, if you can hold the job, because the equipments are not customized. That PVT, CVT, it will have its own shape and everything. So you are going to look at it, and then evaporation is coming up. Okay. So that thing you have to make it. Suppose you have a lathe or milling machine, you know where to hold the job. You must have a job holder or the table and everything. Like this sort of machine is also you have that. And these machines are manufactured by the company. So accordingly, either you make it customized one, paying a high cost, or you accommodate it. So that's why the limitation is always there. Nothing that anything can go one day. Or you can say that I am going to make this type of machine, I am going to who design the interior and supply them. Okay, of course these chips are very costly that you are going to make. Imagine the mobile. Okay, what is the cost of a normal and the latest iPhone? It will be over 1 lakh. Okay, and the chip that you are using then. Hopefully, so India is not famous for that actually. Quality purpose manufacturing in India was not famous. India is famous for coding technology and this, but fortunately we are giving a drive to that in manufacturing. We are very good in giving service, but this is coming. If we are successfully making chips on a regular basis over the years, and the number of factories increase much more, so there will be nothing better than that. Okay, but for that, this sort of technology has to be machines. Even in Jadavpur University, we have not have the fund to purchase such machine, coating machines and all these things. I mean the ready-made electron beam machining setup, ion beam machining, lots of good places there is no fund for that. IIT, some of them I have seen IIT Kharagpur electronics department having such thing. That's a long way. Is must. If there is no investment, nothing can be done. Then there are other ways of making micro components. One is electrodeposition. Again, this is a technology that is going upgradation and applications for chip and all these things. Because electrochemical machining, Faraday's laws, electrolysis, electrochemical machining, electroplating, these were there. There is application somewhere. That same concept is being applied at a micro level. So that is electrodeposition. Electrodeposition, electroplating. Electroplating normals. Electrodeposition micro components. Wafer is there, wafer is there. There will be electrolyte solution and there will be deposition. Okay. There will be anodic dissolution. So if you are stressing on anodic dissolution, it is becoming electrochemical micro machining. If you are doing the reverse, that is a deposition, so electrodeposition. But at that level, so the job is very small, deposition has to be in microns and uniform and everything with the control and everything. So that is electrodeposition. So that again can be done with electrolyte, without electrolyte. Electroless, plating, electroplating. Okay. Okay, I am not going into the details, I will just cover the other phases. Then epitaxy is another such thing where long crystals are being manufactured. A similar type of process like CVD. Then thermal oxidation is a similar thing. You are making oxidized layer on them. But that should not be, like if you keep aluminium, it will be oxidized. Aluminium oxide is formed. But that is not manufactured, micro manufactured. Because it's naturally coming, you do not have any control on the thickness, quality and everything. So control manufacturing means what I want I should get in terms of quality, shape, size and everything. So that has been done. But the structure is different. So you need some metallurgical support, the Faradays, everything, passing of water, oxygen control, chemistry part and everything taken together. So it is far away from our normal traditional type of or non-traditional type of manufacturing in normal cases. Okay. Another very applicable process is casting, which is, we are calling it casting, but because some liquid form is there and it solidifies. Mostly for polymers, where you are putting the material in the liquid form and spreading and then heating and then it solidifies. Here it is shown in a flat way, it may not be a flat, it may be a particular shape. Okay. That's why it is casting and called casting and all these things. But application is very limited. Okay. And this is a very, very popular field and it is the thing to stay both for micro manufacturing, chip manufacturing as well as for nano application, lithography. So it's a combination of applying different beams as well as agents. Okay. So this is the theory that you have the substrate, you have the photosensitive material, you are making a mask that sometimes you want that radiated part to be removed, sometimes you want the radiated part should stay. That's why positive and negative masking and all these things are there, and it happens. Then you have some agent application and like our old photography style actually. So we have then you put it takes time creating the sample and everything, then you do. Of course, all these chips will be costly and manufacturing process. It's not like that your handling time is this much and processing time is that much. Definitely, pre-preparation time, pre-handling time should be very much required for making the thing work actually. Okay. That's the positive basis, negative basis. Sometimes you have the radiation and then after removing that, this part will be removed and you do the agent part. And the other way, negative way, where that is radiated, that portion will be removed, the other part will be removed. And this is quite going on for this sort of chip manufacturing, and there's a probable application in all sorts of nano application. Okay, I'm not going into that. And these are the steps, as I'm telling you, there are large number of steps are required, and there's a time consuming process in the required furnace and everything for that purpose. Okay, then after lithography, so these are the process to look for. Photolithography, etching, not the normal way that it is in chemical machining. It will be very, very precise, very controllable and minute level. Okay, and in some cases we may want isotropic etching and anisotropic etching. That means etching. That means sometimes we want more removal at one part and less removal at the other part. And isotropic means the same. Whether the undercut is also same in both these cases. and there will be chemical reactions and all these things. Again, it can be right. Because equipments are very costly, and sometimes they may not have that. So suppose it is 10 crores, they will charge us 15 crores for that. So they will take it out and then rotate it and again rotate it.
So okay, thank you very much for your lectures from the two senior faculty members in the local university teachers, and definitely we will be able to deliver our work in the respective domain. So thank you very much. Thank you.
কিন্তু আমাদের